today's video we will continue with elementary modes, and we will try to understand or fixate these concepts with the help of a slightly more involved example, again a simple one, but having a few more reactions than what we saw yesterday. Okay. So, can we identify the extreme flux modes in elementary flux modes in this example?
Where do we use these elementary flux modes and extreme path? Like where this is only useful, where this is only useful?
So, it's nothing like that. The thing is, elementary extreme pathways are easy to understand in terms of basis vectors of the flux space, and elementary extreme pathways are easier to compute. Elementary flux modes are a little harder to compute, but both of them are relevant. We will see some use cases in the next slide. But for now, can we just try and evaluate, identify the EFMs and EPs in this diagram. So, now you can actually write down the elementary flux modes and extreme pathways based on the reactions, right. Let us even try to trace them out first. So, this will be an elementary flux mode as well. This will also be an elementary flux mode.
So B to P will be an extreme pathway.
BPP.
So this is an interesting pathway, right? So, okay, anyway, let's write down the. So this is the first extreme pathway. This is R1, R5, R8. Right. Then you have R1, R5, R7, R4. Then here you would have even this, or let us start with this R1, R2, R3, R4. Is that going to operate at steady state? D will accumulate. Needs to have R9 as well.
Then E will also, there is a possibility for E also getting accumulated.
No, this is a single reaction, no? C giving P plus D.
But it's like that, okay.
Oh.
Right? So, that is the catch. And of course, you have this reaction as well. So, this will be R1, R5, R7, R4, R9. No, that will just be R4. Only when you have R3, you will need R4 and R9. Right. So, next you can have, let us try to clean up the pathways. So, the next pathways we will have is, let us start with B, right.
So we didn't have that.
This would be a simple
A to A, C, E, E, X.
right. So, R1, R2, R10, R11, right. So, these are all starting at A. Now, let us look at B, right. So, you will have R8, R6, R6, R10, R11. Or you can have R8, R7, R4, R8, R6, R3, R4, R9. So, we have R1, R11 is there, right. So, R1 to R11 you can go like this, that is taken care of. You can have R1 to R3, R4, that is taken care of, right, which also includes R9, or you can have this R6, R8, R6, R8. Is that that? No. R1, R2, R6, R8. Right. And you can have R1, R2, R6, R7, R4. So you will find that it is easier to enumerate the elementary flux modes, not the extreme pathways. Right. Extreme pathways you will have to like see if they are decomposable and so on, and you will find that some of these can be decomposed and so on. Right. Are there any more left?
I think whatever we wrote now is elementary flux mode, right?
All these are elementary flux modes. Some of them are also extreme pathways. For example, this is very well an extreme pathway, this is very well an extreme pathway, and so on. Right. But there are some non-extreme pathways as well.
So, I'm not clear what is extreme pathway.
So extreme pathway will be, it's non-decomposable. So, for example, if you had something here, you could, for example, this will be an extreme pathway. I mean, an elementary flux mode and an extreme pathway. This will be an extreme pathway and an elementary flux mode, right? But this will be only an elementary flux mode, not an extreme pathway, because you can write it out in terms of this extreme pathway and this extreme pathway. Linear combination, in fact 1 plus 1, simplest linear combination. Right. So let us see, have we missed out anything else? Let us take a careful look. This is done, this is done, this is done, R1, R2, R6, R8 is done, R1, R2, R6, R7, R4 is done. So we have 3, 6, 7, we have 10 EFMs identified. Let us see if that is correct. We may have missed out. There are 11 EFMs, we just seem to have missed out 1. What is it that we missed out? Is this there? R1, R5, R6, R10, R11? R1, I think that's the one that we missed. Right. So now if you see, which of these are elementary modes and which of these are extreme pathways? All of these are elementary flux modes. Which of these are elementary pathways as well?
First one.
The ones on the top, right? Because if you add them up, you can get those on the bottom. So let us see, EM8 is EM3 plus EM6, EM8 is EM3 plus EM6. You add these two, you get this. Fair enough? So like that you can set up all of these.
So, are all EFMs just paths between?
Paths between? They are not paths, right? So they have to honor stoichiometry and things like that. See, you find that, so they are not just graphical paths, right? Because from C, you have to produce P and D. Here you do not have an example of that sort, but imagine if that reaction were reversible, you need both P and D to form C, right? Which is never taken care of in graph theory, unless you do it very carefully, right? The substrate graph won't take care of it. In a bipartite graph or hypergraph scenario, you might be able to do it. But here you also admit stoichiometry and so on. So we've just been looking at a simple example where we are identifying it visually, right? But this actually takes into account stoichiometry as well. If you have 1A producing 3B, you have to make sure that the 3B is taken off into other reactions and so on. So one reaction is possible, but when you have multiple reactions, so the 3B will produce 3C, right? And say 3C reacts stoichiometry in a different stoichiometry with something else. So there is 3C plus D doing something, or like C plus D doing something. You will need 3D coming from somewhere else. So you have to honor all of that. The algorithm is like quite complex. And all of them are like very slow and involve literally some sort of exhaustive enumeration and so on. So most of the EFM algos are relatively slow, and it's actually not the question of the algos being slow. The problem is in most large enough networks, you've got an astronomical number of EFMs. We're like talking about like billions of EFMs and millions of EFMs and things like that. So there are many interesting applications for EPs and EFMs. So Can sugars be produced from lipids? What is the most efficient pathway for the production of a particular metabolite? Right? You can look at stoichiometry and things like that. Right? What is the, if I use this CFM, I'll get X amount of product per Y amount of substrate. If I use this CFM, I'll get Z amount of product per X amount of substrate, and so on. How redundant? So, do you have multiple EFMs between a pair of compounds? Right? So, that will mean it's pretty robust, right? Because you need to disable both EFMs to stop the production of the next compound. How does enzyme deficiency affect the system? Can you identify drug targets, and so on? Right? So, if you have an essential EFM, many of the enzymes in that EFM will be potential drug targets, and assuming it's a pathogenic organism. So, this is Stephen Schuster. He was one of the pioneers of the elementary flux mode approach, and as he says, it's also useful in determining minimal media and detecting futile cycles and gap filling and so on. Okay. So, but the important thing to note is this is again a very useful technique simply because it does not ask too much information. It only relies on the stoichiometric matrix which we already have.
So you can use this to get minimal genome.
You can potentially use this to get minimal genomes, right? So the union of all, no, but finding EFMs is already complex, right? So the union of all your EFMs, all your essential EFMs will be a minimal genome.
No, or extreme part.
Or the EFM involving biomass. The minimal EFM involving biomass will be a minimal genome.
That will be.
All union of all EFMs involving biomass, right?
No. That will need not be minimum, right? So if you have one EFM producing biomass, your job is done.
The shortest here.
The smallest EFM that produces biomass, yes. In today's video, we covered another example to understand elementary modes, a slightly more complex example, and I hope this has now given you a picture of how one picks elementary modes from a given metabolic network. Of course, it gets a lot harder to do it visually the way we have been doing it on a more complex network, and there are many efficient algorithms to do the same. In the next video, we will move on and start looking at applications of constraint based analysis. I will introduce you to some applications, particularly how we go about predicting drug targets in a particular metabolic pathway in tuberculosis.